Okay, hi everybody. So somebody brought it to my attention that we had actually not correctly proved this. Why? Because you can't expand this out and then start cross multiplying right away, because e to the x is not a sum, it is a limit of partial sums. And e to the y is not an infinite sum, it is a limit of partial sums. So this is a complex number, this is a complex number. But in essence, that is what we're going to do, is multiply the partial sum times the partial sum. And then there's going to be some extra terms that are seriously annoying. So let's show you how to deal with it so that we can prove this in reality, really actually prove it. By the ratio test, we know that both sides, like this is a complex number, this is a complex number, this is a complex number. We know that they converge, these infinite sums. The limits of the partial sums converge. So let's give the partials a name, Rm, Sm, and Tm, for the partial sums of this, this, and this. Then the Rm's go to that, the Sm's go to e to the x, the Tm's go to e to the y. By the limit laws, we know that the limit of the product is the product of the limits. That's in our book. And you can prove this pretty easily. If we show that this thing is less than d for every possible d, I think I started using epsilon later, but for every possible positive d, then actually that number is 0. The actual complex number here is 0. And you can see that, like, if the absolute value of some complex number is smaller than d for every positive d, that implies that z is actually the 0 complex number. If it weren't, then it would be here, and this would be a positive number. We could take half of that, and it would get a contradiction. So anyway, this is valid. And if that's the 0 complex number, then e to the x plus y is equal to e to the x times e to the y. So this will be our strategy. Can we show this? For every d, can this be smaller than d? Well, here's this, and here's the partial of the products, and here's the product of the limits. By the triangle inequality a couple times, or the quadrilateral inequality, it is always shorter, or at least it's a tie, to go right across than it is to first go over here, then here, and then here. In inequalities, it's just this. So if we can make this less than epsilon over 3, this less than epsilon over 3, and this less than epsilon over 3, then the whole thing is less than epsilon exactly as needed, where I have now called d epsilon for no apparent reason. Now, this can be made less than epsilon over 3 just because e to the x plus y is the limit of the Rm's. This can be made less than epsilon over 3 just because e to the x times e to the y is the limit of the partial sum, or the partial of the sequence formed by this product by limit laws. So the hard part is here. This is hard. So why is this true if m is big enough? Okay. So eventually we'll take n1 so that m past n1 implies that this is less than epsilon over 3. We'll find n2 such that this is less than epsilon over 3 here. And then we have to find n3 so that this thing is less than epsilon over 3. So can we find it? Well, let's look at it in the case m equals 3 to figure out what is going on. R sub m then becomes this. S sub m becomes this. T sub m, this. Now we can cross multiply, which is what we did before, but with dot dot dots, which was not rigorous. That's a word that means it wasn't correct. It was wrong. Because these things, anyway, okay, so if we expand this part out, we get this. If we expand this, we get this. And you see that you're going to get all these terms over here as well. Like, where will we get x squared over 2? We'll get it from here times here. And so the minus sign will cancel it. So where will we get a 1 times a 1 will cancel this one. So everything will cancel, except what won't cancel? Well, things like this, x squared times y squared will not cancel because there's nothing of degree 4 over here. And if we multiply these together, we get degree 4. Now it will be in here, and what we'll get if we multiply this out is basically we'll get everything of degree 4 that wasn't over here, except we're missing x to the 4th and y to the 4th. So let me just show that real quick. So if I multiply this out, I'm going to get, how do I get x in terms of x to the 4th? I'll get this times this, x to the 3rd over 3 factorial times y over 1. I'll get this times this, which is x squared over 2, y squared over 2. And I'll get this times this. That's also total degree 4, xy to the 3rd over 3 factorial. And you'll see that those would occur. They're in here. This is in here. This is in here. So we have all of these. What we don't have is we don't have this one. And we don't have this one. So I've written it in terms of what we don't have. This whole thing, after cancellations and writing it in terms of what we don't have, is this. Okay? Now what I'll do is I'll take these things and split them off over here by the triangle inequality, less than or equal to. Remember the triangle inequality, if you have an absolute value of some sum or difference, x plus y is always less than or equal to absolute value of x plus x value of y. And same thing with the difference. You can do this if you want, because minus y is the same magnitude as y. So that's what we're doing here. Taking these and putting them there. By the triangle inequality, we split off and we put all of these things and we put them here. Now I've organized them in a very specific way. Some of them I put over here, some of them over here. Why did I do that? Well, we'll see. First of all, notice that the ones I put over here have a degree in x that is bigger than m. So if m was 3 in this case, is my example, then they have degree 4 or bigger in x. All of these have degree 4 or bigger. These ones, though, have degree 4 or bigger in y. And so I split these things into 2 pieces to organize them better. And then I notice that there's a pattern of how many terms there are. So here there's just going to be 3 terms, namely the m plus 1, which is 4, m plus 2, all the way up to 2m, so which is n plus 3, m plus 3 in this case. And okay, so basically let me just fast forward. That whole sum I actually write in sort of symbols like this. So here's the part that I split off. Right there is these that I split off right here. And let's look at it. It's a sum from m plus 1 up to 2m. When m is 3, this is a sum from 4 up to 6. 4, 5, 6 of these things. And that is exactly what we get over here. 4, 5, 6. 4, 5, 6 up to 2m. 4, 5, 6. Okay, so now what do I do is I'm going to notice that, look, there are only 3 terms, and that's m. And in the general case, there will be m terms. And if I take these 3 terms and I replace each of them with their biggest one, which in this case, it might be this one. Okay, why is it that one? Why is this, the 4, bigger than the 5 term and the 6 term? Why is it bigger? If it is bigger, we can just replace each of these by the biggest one, and we get 3 terms, so we get 3 times that biggest term, okay? It's like if you had the absolute value of 2 plus 3 plus 8, that's less than or equal to 3 times 8. Because it's less than or equal to what? 8 plus 8 plus 8, which is less than or equal to 3 times 8. Anyway, that's exactly what we're doing here. Replacing each of these terms by the biggest one. Now, if we choose m big enough, we know that that e to the x plus y converges, so these partial sums go to 0, because it's an infinite sum of x plus y to the n over n factorial. This can only converge if these things go to 0. And actually, by the ratio test, we know that the common ratio from 1 to the next term is going to be eventually less than 1. That's why we can prove it converged, because the uncommon ratio was less than 1 eventually. If that multiplier is less than 1, that means that we have a strictly decreasing sequence of terms. And so if it's strictly decreasing, if we go far enough out, if we take m large enough, then this first term will be bigger than the next ones, because the multiplier is a number less than 1. Okay, so that's why down here we can say that this thing right here is smaller than m times the first term in the sum, which is the m plus first term. Okay. Now over here, we're going to do very similar things. First, we have to understand the sum, and then we have to estimate it and say it's smaller than, this will be less than or equal to, the number of terms will be this number of terms. This is a sum of a bunch of things, something plus something plus something plus something plus something. How many things are we adding? Turns out the answer is m plus 1 times m divided by 2. How do I see that? Well, because up here I have a square it's a 4 by 4 square. Okay, and so there are 4 squared entries in here. Then I get rid of the diagonal, I remove it. That's removing 4 terms. But then I don't want these, there's one term over on here for the upper. In other words, this is the number of terms. And let's check. 16 minus 4 is 12. 12 divided 2 is 6. And there are 1, 2, 3, 4, 5, 6 terms. So that is correct. In general, it will be how many terms in this sum? This sum will have m plus 1 times m divided by 2, which happens to be m squared plus m over 2, which happens to be m plus 1 squared minus m divided by 2. Minus m plus 1 divided by 2. That happens to be true, just because from the geometry I know it's true, but let's check it. M squared plus 2m plus 1 minus m minus 1. That cancels. The 2m and the minus m become an m, and we get m squared plus m over 2. And that is correct. Okay, so anyway, there's a lot here. Now, why can I replace all these different terms with these things? So let's think about that. First of all, let's look at these terms, just for y for now. If y is equal to 2, then n equals 0 gives 1. N equals 1 gives 2 over 1 factorial. N equals 2 gives 2 squared over 2 factorial, which is 4 divided by 2, which is 2 again. Oh, so this is like that. And then it starts going down. This is a better picture. And so there's some value of L, or some index that is biggest, and then eventually they're going to go down. Like here, this is 8 divided by 6, which now is less than 2. And this one is 16 divided by 24, which is now even less than 1. And you see that these are going to go down, and they gotta go to 0. Why do they? We know they're going to go to 0 because the sum of them converges, and if the sum converges, the divergence test says the terms go to 0. So there exists some index, I'll call it L sub y, such that y to the L over L factorial is biggest. And this depends on y. If y was 2, then that index would be either 1 or 2. If y was a half, then that index is 0, because actually it's biggest at 1, and then it's just all downhill from there. So it really depends on y. So there's some index L sub y, and there's some index L sub x such that this is biggest. Okay. Now, By the divergence test, we also know that these go to 0, and so also the xn over n factorial go to 0 as a sequence. And so that means that we can take this thing, which could occur, j is going to occur from m plus 1 to n. And so if we take m far enough, these powers up here, because this thing goes to 0, and because the ratio test says it's also decreasing, the biggest one is the m plus first, just like before. So with this, we'll replace by the m plus first, which is the biggest. And then these actually are trickier. These are trickier, these n minus j, because we can't say they go to 0 because the yn over n factorial go to 0, because these, the exponents can be 0. In fact, they will be a 0, a 1, a 2, a 3, a 4. But luckily, we can still just choose the biggest one. And now, all of these many terms are replaced by the biggest possible term, repeated that number of times, the number of terms times. And so now what do we do? So now we have, finally, almost there. We are trying to understand this. Why can this be made less than epsilon over 3? Well, because of this argument right here. So choose m. Choose n, whatever we are on, n4, such that going past n4 implies that this thing is smaller than, let's say, okay, hold on. What did we want? We wanted this less than epsilon over 3. So let's make this less than epsilon over, divide by 3 again. Epsilon over 9. We'll make this less than epsilon over 9 and make this less than epsilon over 9. Then if you add them up together, you get something that's less than epsilon over 3, which is what we wanted, because we're going to add it to these things, which we already said are less than epsilon over 3. Okay, so why can we make this less than epsilon over 9? Well, choose... Oh, I see. Okay, so this m will cancel an m down there. So let's... didn't even notice that. X plus y to the 1... Oh, this should be absolute value. X plus y to the 1 over m plus 1. Yeah. And then the m cancels that m. Oh, so maybe I need squared. This m would cancel this m, leaving an m minus 1 factorial x plus y to the m minus 1 absolute value. And so this cancels, and now we can choose this. We can choose n4 or n whatever, such that m greater than n4 implies that this thing is as small as we like. Why? Because the infinite sum of these things converges. And so these, by the divergence test, says these go to 0, so we can make them as small as we like. And so I'm not going to finish the details. You can finish the details here. That basically we can make this term smaller than epsilon over 9. This term can also be made smaller than epsilon over 9, because this is fixed, a number. This is going to cancel with stuff down here, so let's show that. So the m plus 1 will cancel one of these, the m will cancel another, and we'll be left with m minus 1 factorial down there. So let's pull out two of these, absolute value of x squared, and leave x to the m minus 1 up there. And then there's a 2, okay, 2 is fine. And then there's this constant, which is y to the ly over ly factorial. And all of these things are constants, right? This is a constant, this is a constant. And this thing can be made as small as we like for the exact same reason as before. The infinite sum of these converge. Okay, so this term can be made less than epsilon over 9. And for the exact same reasoning, except with x and y flipped, so can this one. And that completes the actual proof that e to the x plus y is equal to e to the x times e to the y, using no fancy math, just sums and the triangle inequality and counting. And counting, like how many terms, is the hardest part of this, and also just the sum notation is really hard to figure out that this is in fact the correct expression that matches this, and also just to organize these terms in a certain way. This was a hard problem. Not easy. But it is